Welcome to this lecture series in real analysis. In this lecture, we will learn the algebra of limits, and mainly we will need the following 2 or 3 facts. So in the previous lecture, we proved 2 things. Well, I proved only one of them and left the other one as exercise. So let me recall. Suppose we have a function from a set S to R where S is a set of real numbers, and suppose x0 is an accumulation point of S. Assume that this limit exists and call it L. And define this function f tilde on this domain by replacing if x0 is in the domain, meaning if x0 is in S, then we just replace the value at x0 by L and preserve all the other values. And if x0 was not in the set S, then we are just introducing a new point in this, we are extending the domain of f and defining f tilde as follows. So we did this, and it turns out that f tilde will be continuous at the point x0. So we did this, and conversely, I did not prove the converse, but I hinted at it. I said it in words. Conversely, suppose we have a function on a set of real numbers S, and suppose x0 is an accumulation point of S. And suppose we define f tilde over this extended domain, possibly extended. If x0 is already in S, then it is not extended. But if x0 is not in S, then this is bigger than S. So define f tilde on this possibly extended domain by asking that it takes a value L, some real number L at x0. Sorry, what have I written? At x0. So I've written something completely wrong. wrong. So at x0, you take L, and otherwise you mimic the function f. So for some real number L, you define this f tilde this way. And if f tilde is continuous, then the limit of the function f as x approaches x0 is L. So the converse of this also holds. Okay, so we will use these 2 facts, and we will use the algebra of continuity. Meaning what? If we have 2 functions f and g defined on a set S, and x0 is a point in S, and f and g are continuous at x0, then f plus g is also continuous at x0, f times g is continuous. There is a theorem regarding the ratio of f and g and so on. So these things we will use. And there is this fact about compositions, that compositions of continuous functions are continuous and so on. So we'll use all those facts along with these 2. Okay, so let's proceed. Here are some problems for practice. And now let us get started. So fix a set of real numbers. Pick x0 in R, which is an accumulation point of the set S. And let f and g be 2 functions with domain S such that the limit of f as x approaches x0 exists and is equal to, say, a number L. And for g, it exists and say it is a number m. Alright, for some L and m, then the limit of the summed function, the limit of the sum of f and g also exists as x approaches x0 and is equal to L plus m. Somewhat differently written, we could write this as the sum of the limits. So the limit, so to say, distributes over the sum, right? So if the limit of f as x approaches x0 exists, and same for g, then the limit distributes over the summands. Okay, similarly for multiplication. Okay. So let me prove the first one, and the second one will be exercise. And the idea employed to prove the first one is essentially all we'll do in this lecture. So most of the things I will leave as exercises from this point on. But let me give a proof of the first one. So define f tilde and g tilde as you can guess. At x0 it is the limit of the function f as x approaches x0, and apart from that it just mimics the function f. And a similar definition for g tilde. Okay, and we know by what we recalled, we know that f tilde and g tilde are continuous at x0. Okay, and therefore by algebra of continuity, this is continuous at x0. And just note that, what is f tilde plus g tilde? F tilde plus g tilde is, so to say, the tilde of f plus g. I mean, this is, we haven't defined what that means, but this is just a suggestive statement, so let me not write it. So from here it follows, since f tilde plus g tilde is continuous at an accumulation point of the domain of f plus g, the limit of f plus g as x approaches x0 is the value that this takes at the point x0. So therefore this limit is the value of f tilde plus g tilde at x0, which is L plus m. So we are just using what we recall, the converse part. F tilde plus g tilde extends f plus g to this set, and f tilde plus g tilde is continuous at the point x0. We just argued that, and therefore by using the converse recalled in the beginning, we have this conclusion, and that proves part 1. Part 2 holds very similarly, and that's it. I mean, we are just using algebra of continuity. If you like, you can prove these two things from first principles of limits. And it's a good exercise if you're not yet comfortable. It's a good exercise in epsilon and delta. But we are just leveraging on what we have already proven. Okay, so let's move on. So this time we have a function from a set S of reals to reals, and a function g from a set T of reals to reals, and these will be composable functions. So let me write the hypothesis. So assume image of f is contained in T. So if I were to draw a diagram somewhat schematically, I would say, think of this as S, and then we have T. Both S and T are set of real numbers, but we are drawing it in this weird way. And F maps S inside T, and G maps T to the set of real numbers. So this is a set of reals, this is a set of reals, but it's just that F takes all of this inside T, and G maps this inside R. That's what this says. Okay, and let x0 be an accumulation point of S, and y0 be an accumulation point of T, such that this is equal to y0, and also assume that this limit exists and is equal to some real number m. Then the limit of the composed function, limit of the composite as x approaches x naught is m. It exists and is equal to m. So to justify this somewhat heuristically, x naught is an accumulation point. I'll just think of it as lying somewhere here. As you come closer and closer to x naught using the points of s, you come closer and closer to y naught. Right? The statement can be thought of as you come closer and closer to x naught, you come closer and closer to y naught. Y naught is an accumulation point of t. I'm just kind of thinking them as lying on the boundary. Okay? And what does this say? It says as you come closer and closer to y naught, under the function g, you become closer and closer to m. So if you just apply this two-step process, you come closer to the point x naught, and therefore once you apply f, you come closer and closer to y naught, and then you apply g, you come closer and closer to m. So this is not some extraordinary thing that we have written. But to justify it, we'll just use the previous strategy, and I will not give full details. Just define f tilde and g tilde as they should be defined. Right, that is clear. I mean, not clear. I mean, we are defining it this way. What is clear is the following. By our hypothesis, we know that f tilde is continuous at x naught and g tilde is continuous at y naught. Therefore, by what we learned from our study of continuity, we know that this is continuous at x naught. And now, again, this is a function on this extended, possibly extended domain, possibly extended version of S, where this function extends the composite function, right? The value of this function at all points of S, except possibly at x naught, match with the value of the same for this original composite. And this happens to be continuous at x naught. So skipping some steps, but I'm sure you can fill them up. It follows that this limit exists and is equal to this thing, right? Which is equal to m, and that finishes the proof. So it's the same proof or same strategy that we employed in the previous one. Okay. Now, this time again, we have a set of reals and x naught is an accumulation point of it. And let f be a function such that the domain of f is S and this doesn't vanish anywhere. And it also achieves a limit at the accumulation point, or as you approach the accumulation point. So this is for some non-zero L. So it approaches a limit and a non-zero limit. Okay. Then the limit of the inverted thing is the inverted limit. And all of these things are meaningful. This is never zero, so we can write this. And L is also non-zero, so we can write that. And what is the proof of it? Just use the previous proposition with G as, right? So this is T in the previous proposition, and use this G and apply the previous proposition. Immediately you'll get this. So I'll not write the details. Okay. Another thing. We have a set of reals and x naught is an accumulation point of it. And we have two functions on S such that we have limit of f exists as x approaches x naught. Same for g, it is equal to some number L, and for g it is some number m. And assume gx doesn't vanish. So what are the assumptions? gx is never 0 for any x in the domain, and the limit m is also non-zero, then the limit of the ratio exists and is equal to L upon m. Right? So this is just by multiplication version. So what we saw in the first slide, that limits are well behaved under sums and products. So you just need to use that the limits are well behaved under products, and the previous slide. So if you consider the function 1 upon g, so we have this function 1 upon g from S to R, and by the previous slide we know that this is the case. Or maybe I'll write it this way, 1 upon g of x, it's the same thing. This is 1 upon m by the previous slide, and we anyway are given the following. So you just use that limits behave well under products. Right? This implication is immediate from well behaviorness of limits under products. And yeah, this is it. This is just a rewriting of what we desired. So that proves limits theorem regarding division. Alright, so these are some basic things. I don't want to dwell on them. And now we can start derivatives from the next class. Alright, so as usual, like, comment, share, subscribe, and I will see you next time.